So today's topic is filter design. And by filter, I mean any system which picks content. Or you can think of it as reducing the volume of information. So this is recommendation systems, this is news aggregators, this is the Facebook news feed, this is Twitter's algorithmic suggestions, anything which has to rank results. Search engines as well can be considered a type of filter. These are the recommendations for what you should watch on Netflix and what you should buy on Amazon. This is fundamental technology for handling information. And basically all of our news consumption goes through filtering algorithms at this point. So we're going to talk about why we do this. Then we're going to look at quite a number of algorithms for doing it. Then we're going to add humans back into the system because real filtering algorithms have things like teams of thousands of comment moderators, for example. Then we're going to talk about some classic problems or concerns with filters. How many of you have heard of the idea of the filter bubble? Yeah. So we're gonna talk about polarization and filter bubbles. Try to get some clarity on that debate. And then we're going to talk about filter design. What is it to design a filter? What do we want a filter to do? And then you'll have an assignment, which is to design a filter. Filtering. I'm showing you this picture of a newspaper to make a few points about what a filter does. So if you look at a standard newspaper, you've got a big headline here, and then a subhead here, and then smaller stories here, and then of course stories on the following pages. One of the reasons I'm using this particular headline is in part because I used to teach this course in Hong Kong, but in part because you may not have seen this headline if you were living in Europe or America at the time. You would have seen this news, but it might have been page 2 if you're in Los Angeles, whereas it's front page if you're in Manila. So the point I'm making is that there has always been filtering or prioritization in news. That's how we decide what should get the most attention. Humans have always done this. And actually, there's starting to be research comparing what humans do and what filtering algorithms do. This is also a filter. This is Google News from, I guess, a few days ago. And, it's all Kavanaugh all the time right now. So think about that for a second. Of all of the things that happened in the world yesterday, when I go to Google News, why do I get that one? Right? Now, of course, I think it's undeniable that it's an important story, but there's lots of important stories. And outside the US, this is going to be a much less important story. So that's a filter as well. And we know a little bit about how this is done. We talked about the clustering algorithms that produce the groups of stories and categorize them by topic. What we didn't talk about is the ranking algorithm that picks which story goes at the top. So think of it that way. That's what we're going to talk about today. How do you know which story goes at the top? Here's the Facebook news feed. This was actually from a Business Insider editor. It was actually quite hard to find a picture of someone's news feed. Like, who's willing to post their news feed, right? But of course, the news feed is a filtering algorithm, possibly the most significant filtering algorithm at the present time in terms of its effects on society.
Why did he post that, actually, now that you mentioned nobody
Oh, it was an article about the Facebook news feed. And so they needed an illustration, and so they had a brave volunteer, I guess. Mine were too stupid to post. Here's an old graphic. It only goes to 2015 or so, but At the time, it was 300 hours of video per minute uploaded. I'm sure it's much higher now. So you can do the math here and think, well, how many television stations were there in the 20th century? Right? Commercial television transmission started late 30s, 40s, earliest. We might have had a few dozen channels at peak. So you start working this out. Let's say we have 50 channels times 100 years, and you find that the amount of video on YouTube exceeds the amount of broadcast television in the 20th century by multiple orders of magnitude. And we're probably closing in on 1 million times more video. So this is a huge amount of information. And of course, it's not just video and news. Public information is produced at an enormous rate. So every time a public company takes certain types of actions, the executive buys stock, they make an acquisition, that sort of thing, you have to file a report with the SEC. So there are 10,000 such reports filed every day. Imagine covering this stuff, right? So imagine you work for Reuters or Bloomberg and you have to watch this stuff. Even if you have a team of 100 reporters doing it, that's still a 100-to-1 ratio. They can't cover every, so they have to pick some set of this to look at. So implicitly or explicitly there's a filter happening here. And this is the AP's output. The AP only has a few thousand reporters, so actually how they get 10,000 stories a day is write-throughs and translations and syndication. They probably produce a couple thousand original text stories a day if you don't count this sort of stuff. But I got these statistics a number of years ago by talking to one of the engineers on the platform which routes all this information. I want to try a little experiment with you. I want to estimate the filter aperture. And by that I mean, how many orders of magnitude do your personal information filters throw out? So to do this, we need two things. One is, how many items of content per day do you consume? So how many links do you click on? How many articles do you read or videos do you watch? I mean, what's the estimate here? Anybody want to hazard a guess for?
Can we define? Yeah. What is an item?
Let's pick it. Let's say an article you read.
An article you read from top to bottom. Or an article you open.
Let's just say the article you open. It actually doesn't much matter what you pick, because if you change the definition, you'll change it by maybe 1 order of magnitude. So let's say an article that you open. So what are we talking about? How many a day? 10? Any other guesses? Was that 15?
No,
10. 10? Okay.
I don't know. 15.
Yeah. So it's on the order of like 10, 20, 30. It's not 100. It's not 2. Okay. So we can say conservatively 10 items a day read. I suspect that it's a little bit higher. I suspect that by the time we count the cat videos, it's going to be more like 20 or 30. But we're just doing order of magnitude estimates, so it actually doesn't matter if it's 10 or 50.
So what about like headlines also that you kind of see while you're choosing what to read?
Yeah, maybe you see 100 headlines. Yeah. But let's call it 10. Okay. So now we have a somewhat harder estimate. So this is what makes it through your personal system of filters, which is a combination of what humans have picked and put on these sites, and what Facebook has chosen, what Google News has chosen, what the recommendation system of the New York Times has chosen. So most news sites now have personalized recommendations. Right? So the combination of all of these filtering systems gives you that. So now, let's say you're reading only new items, right? Let's simplify this problem and say you're only going to read things that were produced that day. You're not looking at the back catalog. How many articles are produced a day? So that's a hard thing to estimate. We're gonna break that down a little bit. Again, we're just looking at orders of magnitudes, and we'll put some ranges in this. How many publishers are there that you might read? So I imagine you're mostly reading in English, so we'll just restrict it to English language publishers. Are there 1,000? Are there 1,000,000? How many publishers are there? How many people putting content on the web?
A few thousand?
What's that?
A few thousand?
A few thousand, yeah. Anyone other guesses?
Any publishing any content?
Well, publishing any of the content that you might click on, yeah.
No, publishing like art, publishing official.
Well, it's got to be the same count. It's got to be the same universe as that, right? So publishing stuff that you read.
Oh, specific to us then.
Well, or that you could read, right?
Yeah, that changed it.
But if you're not counting videos here, then we're not counting
We're
videos.
trying to estimate the amount of the total items.
Yeah. How many items you could read if you read them all.
Yeah.
So don't sweat this too much. We're going for orders of magnitude here, right? So I'm going to say 1,000 to, I think we have 10,000 publishers. Do we have 100,000?
No.
Yeah,
Depends on
blogs,
what
all
Yeah.
this stuff.
Blogs,
I mean,
yeah.
it's up to
Yeah.
1 billion, I think, but.
All right. So let's just put the uncertainty in here, right? So we're just gonna. This is very like the what's it called? The Drake's equation, right? You're trying to estimate the number of civilizations in the universe. We get these really wide ranges, but that's okay. We're looking for order of magnitudes. Okay. So then, how many items a day on average does a publisher publish? No, the AP is big. It's one of the largest news organizations in the world.
Like 100.
Okay. Yeah, I think it's probably smaller. I'm going to say 10 to 1,000 because there are big ones as well, right? So if we multiply these two together, then we get, so that's 10 to the 3, that's 10 to the 1 on the low end. So we get 10 to the 4 to, what is that, 10 to the 5 times 10 to the 3, 10 to the 8 items published day. 10 to the 4 seems really small. There's definitely more than 10,000 a day. So I'm going to say that we do not have that case and call it 10 to the 5 to 10 to the 8. Because what we know one publisher alone does 10 to the 4. So then divided by 10, so then divided by 10 items day equals 1 over 10 to the 4 to 1 over 10 to the 7. So that is the filter aperture. Right? That is how much narrower the funnel or the sort of business end of the filter is, the end that you read compared to the stuff going in it. Right? That's measuring this width. So to me, that says you have no hope of having a representative sample. It doesn't matter what you do. The output of the filter is not going to give you a very good picture of the input to that filter. So there's this idea, I hear journalists and other sort of information professionals say this a lot, right? Everything you need to know about what's happening in the world, right? You're gonna read this news source, you're gonna be an informed person. No way. Absolutely not. It is not possible to keep up even with what makes it as a newswire headline, right? If you wanted to keep up with what an international wire service is producing, so if you want to read the AP or the BBC or the Reuters or the Bloomberg feed, you're going to be doing nothing but reading those stories all day. And that's just what the major wire services are producing. We're not talking local news or anything like that. Okay? So nobody is an informed citizen in the classic sense of like knowing what's going on in the world. Instead, we have these systems that give people a little piece of what's happening. And so we have the very complicated problem of what piece do we give them? And that is one aspect of the filter design problem. Okay? But I want you to think of this tiny little funnel. So on average, you get to pick 1 in a million. So which one out of the million do you pick? Right? And even a random sample is pointless because if you pick 10 random items out of 10 million items, there's more than 10 topics in the world, so it doesn't matter what you do, you're just going to miss everything. On the bright side, that's normal. This is how humanity has always operated, and it is possible to be more informed than at any other time in history, but you're never going to, know everything.
How much of these orders of magnitude would be duplicates of the same story?
I don't know. I mean, you could knock off an order of magnitude if you want. Right? The only thing I'm really trying to say is that it's not like you can read 1% or even 0.1% or 0.01%. You have to start getting into the 1 in a million range to get estimates. And actually, I think this is a little low. I think when you start adding in social media posts and you start adding in foreign language media, I think we get a few more orders of magnitude. So given that we have this tiny filter aperture, I want to start talking about algorithms to select some tiny subset of things to show you. And we're going to build this up from some pretty simple algorithms to some pretty complicated algorithms, culminating in the underlying architecture of the New York Times recommendation system. But we're going to start with comment ranking. So any discussion system, let's say Reddit in this case, because that's actually the algorithm we're going to look at, needs a way to rank comments or rank stories, whatever the unit of analysis is. So they have voting, usually. And the idea is that things that are voted higher go to the top of the list. Now, this is actually not a very good comment ranking algorithm. Just straight put the items with vote at the top fails in actually a pretty bad way. Can anybody guess the way in which this fails?
Comes an echo chamber.
Yeah, so it's those things which have a lot of votes appear at the top, so they get voted on more. The problem is that you don't actually even get a chance to vote on the stuff that's even below the fold, right? So for example, we know there's an enormous drop-off if you have to go to the second page of Google search results, right? So that means, at most people are going to look through 10. There's actually a bunch of documentation which is discussed in an article that's linked from the syllabus on how Reddit's comment and story ranking works. And originally it used this algorithm, which is now known as the HOT algorithm. And it's called the HOT algorithm because it's got this time-based component. So think of it here, right? A is when it was posted, and B is the current time. We take this time variable here, this TS thing, and then we do a calculation of the number of upvotes minus downvotes. Y is basically just a sine function, but basically we have the time divided by some constant. So as the article gets older, it falls down in the rankings. And Z is a function of, basically it's a clipped upvotes minus downvotes. It doesn't let if something has a lot of downvotes, it doesn't let it go below the 1. So you can't make things massively negative. So basically it's this thing where it's, log of the number of upvotes plus a decay factor over time. So this is about as simple a filtering algorithm as you will find in practical use, right? So it's based on votes and time. Makes things decay a little bit. So far, so good?
Is that their current algorithm?
No. This is the old algorithm. I think this one is still used, or you can set it to be used for stories,
Okay.
but they've decided that stories and comments need different rankings. But the nice thing about Reddit, and the reason I'm using it as a teaching example, is it's open source. So you can read the source code, and people have commented on it, including Randall Munroe of XKCD wrote a long article about, actually pushed for the ranking change that we're going to talk about, and wrote a long article about why. The new Reddit comment ranking algorithm is based on the idea that you want to approximate the percentage of upvotes, so here I've drawn them as green dots, that you would get if every user voted. So let's say there are n equals 16 users. You want to know how many of them voted positively. That's that V number. So as if you had every single person weigh in. Of course, we can't have every single person weigh in. We only observe some fraction. And the problem that we face is that when you observe only a fraction of the votes, the proportion estimate can vary dramatically, right? So if you only have 3 people voting and they just happen to really dislike it, whereas actually most people like it, you'll actually get the wrong signal. So what we do is we account for the uncertainty in the observed vote proportion. And ready for this? Oh wait, no, it's the next slide that has the big equation. Oh yeah, so here's what I was just saying, right? Depending on which users we see, we can get dramatically different upvote proportions. So we're talking 70% versus 20% here. What we do instead is we compute the confidence interval of the observed vote proportion. So you've all seen basic sampling theory, right? At this point, margin of error on a poll. Anyone? Oh, interesting. Okay. None of you have had a basic stats class. You have. Okay. A long time ago. Okay. But you're familiar with the idea that you can compute the interval in which the true proportion is likely to lie, right? There's formulas for doing this, or you can do it with resampling techniques and so forth. Well, okay. This is a scary looking formula. It was actually derived in 1915 by this guy Wilson. And what it is it's just an approximation to the confidence interval. And it's a big formula, but notice there's only a couple variables in it. We have p hat, which is the observed proportion of upvotes. We have n, which is how many people voted. And then we have this thing, z alpha, which is it's the confidence interval. It's do we want a 5% or a 10% margin at the sides. And what it actually is the integral of this area. The main thing to notice here is that we have the observed proportion plus a correction factor, which is likely to be very small because as n increases, this gets smaller, and then plus or minus this thing, right? So it's the observed proportion plus or minus some range. Apparently, this is what Reddit actually uses. And what they do is they rank the comments by the lower bound. So if we've had 3 people vote on it, we don't know what would happen if we had everybody vote on it, but we know that it's going to be, let's say 2 out of the 3 voted up. So we say, well, 66% is our best estimate. but because only a few people voted on it, it's like 66% plus or minus 20. So we're going to say minus 20. In other words, it's at least 46% upvote, and we're going to use that to rank it. And as more people vote on it, that confidence interval narrows. So as more people vote on it, n increases. And you can see all this stuff has n in the denominator. So n, n, n. So the confidence interval shrinks, and the lower bound estimate converges to the observed estimate as more people vote. We gradually rank it closer and closer to the actual portion. So in other words, we penalize comments where we don't have a lot of votes to prevent them from always dominating the top of the listings. We don't let something that has 3 votes and 100, we don't classify it, rank it as 100% positive votes if we only have 3 votes. All right?
So we've thrown away the idea of time then? Where's that?
We are,
I think that from the
yeah.
explanation, the time part was that as people will upvote it, the time part would make the ranking change, but they don't explicitly have a time on it as such.
Yeah.
That
So
was
right. So for stories, they still have time because they want stories to disappear. But for comments, they use this non-time-based algorithm because they want them to sort of stabilize it, like bubble the best comments to the top. So this scary formula notwithstanding, the scary formula is not important, right? You can get nearly the same effect with basically any formula that penalizes items that don't have a lot of votes yet. But by looking at this comment ranking system, we can see all of the basic pieces that we can start to assemble to build a filtering algorithm. A more sophisticated filtering algorithm, this is called collaborative filtering. How many of you have heard of this? Okay, so collaborative filtering is how Amazon generates the product recommendations. It's basically people who bought this also bought that. It was originally applied for email filtering. And the idea here is that we look at the pattern of things that you clicked on, or that you liked, or that you gave a high rating to. We have some positive signal from each user, and each user only looks at a very small number of items. And then we try to recommend to figure out whether you would like a new item by saying, well, who else rated things in a similar way to you? And what did they like? So you can think of it as a 2-step process. We take your likes and cluster you with other users who like similar things, and then ask what else did those users like. So here's the setup. We have a data structure called the user item matrix, and this is a fundamental data structure in filtering algorithms, right? So we spent the last 2 classes talking about the term document matrix. We're going to spend most of this class talking about the user item matrix. And in this case, users are rating movies. So I guess we have a 1 to 7 star rating in this example. This and subsequent diagrams are from the reference in the syllabus. And what we're trying to do is we're trying to do an out-of-sample prediction. So we want to know how user 5 feels about a movie that they haven't rated. And then in principle, to build a recommendation system, what we do is to generate the recommendations for user 5, we guess their vote on every single movie and we show them the top 10. Right? Or that's one simple filtering algorithm, right? So what I'm trying to convince you of is if we can solve this problem of guessing how one user feels about one item, we can use that primitive to build a filter. So we're going to look at a variety of ways to do this today. But this is what Netflix does. This is what Facebook does. This is what Amazon does. This is what everybody does. And it gets, like all of these algorithms, you get this basic algorithm and it gets sort of arbitrary, more complicated. But this data structure is fundamental. One of the things I want you to notice here is that unlike all of the work we just did on text analysis, we have absolutely no content in the algorithm. Right? We are not analyzing what is in each movie. Or we are not analyzing what the product is. And this was very important for Amazon because, I mean, books, sure, you can do text analysis and cluster them. Movies, okay, we're starting to get to the point where we can do video content analysis. But hairbrushes, batteries, tripods, right? How do we do content analysis on these things? We can't really do it. And so this is an enormous advantage of this technique because it doesn't require any knowledge of what the item is. Another thing to notice is that the user item matrix is mostly empty. And so the algorithm has to account for that. And you want to be a little bit careful to make sure that, to distinguish between the user never expressed an opinion and the user didn't like it, right? So I saw that Facebook post and I did nothing versus I never saw that Facebook post are two different signals. And sometimes it's a little tricky to build the algorithm such that they are differentiated. So again, here's the setup for this. We have this user item matrix. We want to predict the vote of one user on one item. And then if we can do that, then we just take the top items and we have our filtering algorithm. So the core logic of this algorithm is that we want to suggest similar items. So if we had a similarity metric between items, then what we can do is we can take the items that the user has previously said, hey, this was great. I loved the 5-quart pistachio ice cream product that you sold me. And we should be able to say, hey, wait, what about 5 quarts of strawberry ice cream? That's pretty similar. That's much more similar than a miniature monster truck set. So let's recommend you the ice cream and not the miniature trucks. So again, we're talking about a distance metric. But the only information that we have about these items, again, we have no notion of the content, is how people rated them. So what we do is we construct a similarity metric based on how different users have rated the same item. And rating I'm using very generically, right? It's any sort of feedback signal. It could be purchase, it could be click, it could be like, it could be commented on, it could be shared. And in practice, real algorithms use a variety of these signals. So here's what we do. We define a cosine distance-like metric between the ratings on two items. Here they've notated it Sij. And it has to be sparse because most users won't have rated most items. You can see those dashes there. We're looking across all users. So the idea here is that the items are sort of implicitly sorted into types. You can think of it like, ice cream is a type, and sunglasses is a type, and action videos is a type. And we have no idea what these types actually are, although of course when you have this data you can start to visualize them through clustering algorithms. But we can figure out if two things are the same type by looking if they got the same ratings on the assumption that users have types of things that they like. So here's the actual formula. This should be super familiar. It's again from that paper. Cosine similarity, right? Two vectors. In this case, they are vectors. I and j are vectors of the rating for two different items across all users. Exactly the same idea. Notice that users who have not rated an item just drop out of this formula. We only compute this formula over pairs where both users have rated something. This, by the way, is one of the keys to efficient implementation. We may have a billion users, and Facebook has a billion users, but this is very sparse, right? We only have to do this over the posts that both users have engaged with. And in fact, there's a bunch of distance metrics we use. This is a version of cosine similarity where we just subtract off the average rating. And what we're doing there is we're adjusting for, think of it as adjusting for the grumpiness of each user. Like, you know, a user who really likes something may give it 5 stars or they may give it 3 stars. And if they dislike it something, you know, you may give it 4 stars, like when you kind of, you know, if you really don't like your Uber driver, you give them 3 stars, right? Well, maybe some people who really don't like a movie give it 1 star, or maybe they give it 3 stars. So we're just normalizing. And it sort of goes from there. You can sort of build up more complicated similarity metrics, but they're all the same idea of looking at all of the ratings on one item. And then, when we actually want to generate a recommendation, right? So we're trying to fill that one item, so PUI, the prediction of user use rating on item I. What we do is we take the weighted average of the rating that the user has given for all other items. So that's the RUN, right? So the user's rating on item N, so we're summing over N, where N is every item that they've rated. And we're saying, or sorry, N is every item. And we're saying what is the similarity of the item that we want to know about, which is I, to the item that they've previously rated, which is N. And then the bottom is just a normalization factor, right? So we are weighting the rating they gave each item previously by how similar it is to the item that we want to guess. So when we run this algorithm, we'll find out that they gave 5 stars to the tub of pistachio ice cream, and you know, they gave some rating to the sunglasses that they bought, but we don't really care about the weighting that they gave to the sunglasses because the sunglasses are not very similar to the tub of strawberry ice cream. Whereas the strawberry ice cream and the pistachio ice cream are very similar because people who liked one tend to like the other. And so we mostly interpolate from the weighting on the ice cream. Yeah?
And the similarity between the items that we have is like dependent on how you set it up. Like you can say that ice creams are similar to each other.
Well,
and toys are not similar to ice cream. Because
no, you don't set it up. That comes out of the algorithm, right? So the similarity is computed by asking, do these 2 items have similar ratings across users? So you don't have to tell it. This is the big advantage, right? You never have to tell it that there's ice cream and sunglasses and toys. It figures that out automatically by saying, oh, well, people who like this like that, and if people who like one type of ice cream tend to like the other types of ice creams, then it will figure out that ice cream is a category. So this is an example of latent structure, and we'll actually make this a little more rigorous a little bit when we talk about matrix factorization.
I guess I'm not able to understand how it will recognize which items are similar by themselves.
Okay.
Assuming that everybody rates like 2 completely unrelated items in the same manner.
No, everybody relates related items in the same manner. That's the key, right? So let's say we have different types of ice cream, and we never tell it that these are ice cream. It learns that, and then these are toys. Let's say cars and crayons. And then these are users. Okay, so we're just going to look at the two user case with a couple different sets of items. So let's say user A likes ice cream and user B likes toys. What you're going to have here is 5 stars for all of the ice cream and 0 for the toys and vice versa. And then you have let's say you add a new ice cream, right? You start selling a new flavor, lime sherbet, okay? And you want to know how similar is this lime flavor to all of these other things, which is this Sij we're trying to calculate. Well, before we can know that, we need to get some information about how the other users have rated it. And what we discover is that user A gave this a 3 and user B gave it a 1. And then we ask, well, this vector, 3, 1, right? So, oh dear, I've transposed this from the diagram there. That's using columns for user ratings. How similar is it to each of these items? And does it look like this vector? Right? Does it look like this? Or does it look like this? And the way we compute that is cosine similarity. So we take the dot products with each vector. So here, let's actually do this. So this is
Oh my god, I'm so sorry.
3 times 5 plus 0 times 1. This is 3 times 0 plus 5 times 1. So this is 15. This is 5. So what we find out is that this new flavor is much more similar to the ice creams than the toys. And the reason we know that is because the users tend to like one or the other. Does that make sense? Yeah.
Just after that,
Sure.
one of the, I don't know where I read it, but one of the, when they started using matrix factorization, one of the things they found out was that people who bought diapers for kids also bought beer. So the items weren't similar in any way. It was just that users were rating them or buying them at the same rate. So the system just said that if you bought beer, you were probably likely to also buy diapers. It had nothing to do with like the item. It had to do only with users who bought them or users who rated them. So it has nothing to do with the content. It's just that whoever reads similar things, it knows that all of these go together.
Right. Right. So I've been saying type of item, but it's exactly, it's not really type of item. What it is items that gets a certain type of ratings, right? It is, you are clustering in rating space. So if 2 items tend to be rated the same way by different users, then they'll be clustered together, even if they have nothing to do with each other. But that's fine, because all you're trying to do is predict a new rating.
So even in this case, if crayons and strawberry ice cream were like, they could go together, and like lime would then be like whichever has like, so then you would say if somebody bought crayons or strawberry ice cream, you would recommend lime, but you wouldn't recommend it if they bought pistachio.
Right. So it could turn out that it's not that things aren't grouped by ice cream. It actually turns out that people who like green crayons like lime ice cream. Right? Maybe people have their preferences based on color and not type of objects. Like who knows? And we'll find interesting surprises like the diaper and beer issue.
Yeah, they kept saying that in class, and I was like, cool, but
Diaper and beer.
yeah,
Yeah.
they just quote that like AI. This is an example, and I'm like,
Yeah. You know, I've never chased down the original source for that. It's one of these like AI urban legends. Except we didn't used to call this AI. The word is getting bigger. Okay, so that's the idea. We're trying to find items that have similar ratings. We're going to go sort of take a next step here. So I've showed you a user item recommendation first because I think it's a little less abstract. What we're going to do now is talk about doing the same thing as matrix factorization. So you will recall that we looked at factoring the term document matrix, and we called the hidden factors topics. In this case, the hidden factors are, you can think of them as topics or type of object. But the idea is this. Okay, so this is the user item matrix, and items go this way, users go that way, and now I have to remember how to do matrix multiplication again. Is that right? Yeah, okay, good. So then what we have here is items and users. And now what we're doing is sort of a hypothetical model, right? So we are saying that there are some number of, let's just call it topics, right? Or types of objects. Because we can use this for anything. We can use this for ratings or articles or whatever. Let's call it topics. And this should look really similar to when we did matrix factorization for topic modeling. And the idea is that each user is interested, and we'll just use zeros and ones for the moment, in some set of topics. So this user is interested in politics and bees. And then each item also has a certain set of topics. So this is a story on politics. Actually, this row is the politics topic, right? So let's say this is an election. And this one, which has the same pattern, this has both politics and bees. So this is about environmental regulation on honey in the honey industry, okay? So it's about bees and politics, so it has a 1 in both places. And then what we say is to generate the observed user item rankings, and here we're just saying 0 and 1. Think of it as click, didn't click, buy, didn't buy, like, didn't like. This can all be extended to more general cases. We're saying, well, how the way that we get this item, so user I, item J, is we multiply through all of those users' topics for the corresponding position in the matrix, right? So it's this item and this user. So what is this? Well, this is an item that's about bees. And so when we multiply through, we get a 1. So that's the idea. The idea is we're saying, you know what? I don't believe that the elements of this user item matrix are truly random. I don't believe that what's here and what's here and what's here are actually completely independent. We can't believe that because otherwise we would never be able to make a prediction. We're saying, I think there's structure. And I think the way that there's structure is I think that items have topics and I think that users like topics. And so I want to find the smallest set of topics that captures this structure well. It's the same idea with words and documents, only now we've got users and items. So going back to this slide, okay, so here we go. We're going to break this down. Matrix factorization, that's what we're doing, finding factors in matrix. We represent users and items in a shared, latent, low-dimensional space of dimension k. So that k is here, k topics. Okay? Latent. This word latent means we don't observe it, but it's behind what's happening. You can think of this as like, this is what's happening, this is the underlying reality that is generating what we observe. In dimension k, user I is represented by a latent vector ui out of rk. So here's user I, here's ui, there's that vector out of rk. It's a k-dimensional vector. And item j by a latent vector vj out of rk. So here's the latent vector for the item, that's the v. And then we form a prediction of whether user I will like item j with the inner product between their latent representations, rij, which is this, which we get by taking the inner product, which is a dot product, of these two latent vectors. So far, so good? Hopefully I've translated the gobbledygook here.
So should we expect one of those topics to relate to be the beer diaper topic, right? They're like stressed about having kids. Is that?
Yeah, exactly. Right. So the beer diaper topic is baby stress, male baby stress, maybe. Yeah. Right. Maybe there's a chocolate diaper topic. I don't know. Okay, so that's where we're going with this. And you can build a recommendation system out of doing this, right? So it's basically the same thing as we were doing before, right? Where we had this user item matrix. It's just a little more principled. In particular, there is this weird thing here where what we're doing is we are predicting the ranking of a user on an item by asking what are the items that are similar to the ones that have already ranked. You could predict the ranking on a user item pair by asking, well, who are the users similar to this user? You can actually run this algorithm either horizontally or vertically, as it were. And matrix factorization just avoids this problem because it's a little more mathematically grounded. And if you take the hit of dealing with matrix factorization, which is, you have to run an algorithm to compute this factorization. If you're okay with doing that, then you get a much more mathematically straightforward prediction that sort of solves this problem of, well, do I predict the rows from the columns or the columns from the rows? To do this, we have to compute the factors. And there's an iterative algorithm that sort of bounces back and forth. We'll see in a second. It starts random for these factor matrices and then computes the user topics given the item topics, and then computes the item topics given the user topics. And the idea is to minimize the difference between the predictions and the observed predictions. So this term here, Rij is what we've actually observed, the ratings of I on j, and then U transposed Vj is how we form the prediction. That's where we take that inner product. And so if we sum over all item pairs and take the square, what we have is the error between the predictions and the actual, and we want to minimize that. And then this stuff is regularization, which I think we've seen before. And that just forces the solution to have as many zeros as possible. Because we would like these matrices to be sparse.
UI VJ is, I guess, it's the...
UI is the
Okay.
topics for the user, VJ is the topics for the item.
And RIJ is what you observe, like a new thing.
Yeah. It's the actual data that you have on who liked what
Okay.
or bought what. And this is sparse, right? So, which is important because if we have 1 million users and 1 million items, then we have 10 to the 12 RIJ pairs, and we don't want to compute matrices with 10 to the 12 elements in it because we can't fit that in memory. So there is another way of looking at this, which is looking at it probabilistically. We've talked about this in terms of, we haven't really, all we've really done is sort of played around with matrices a little bit. We haven't really talked about a probabilistic model at all. And there's some advantages to talking about a probabilistic model, because if we have a probabilistic model, then we can do probabilistic inference, which is a hugely powerful and well-developed set of machinery. To start talking about this, I'm going to introduce this plate diagram, and because this plate diagram is going to be part of a plate diagram of the New York Times recommendation system, which is it's going to be a little freaky, but we'll build up to it. The idea is this. So again, remember that a filled circle means we observe something. So that R, user rating of items, that's the data, that's the input to the algorithm. It's the only thing we start with. And then that box around the R, where it says I users, means we have ratings for I users and J items. And that overlap between the boxes, that means we have a total of I times J items. And we're saying that there exist, but we don't know the topics for each user and the topics for each item, which is the U and the V. And there is, if you like, the regularization. Okay, so regularization in an optimization algorithm becomes a prior when you look at this in a Bayesian context. Has anybody run into this idea before? Okay, so a regularization parameter of this form, when you turn this into a probabilistic inference problem, it's actually a prior which says that the distribution of values in this matrix, these UI and VJ entries, are going to be around 0. And the width of this thing is going to be like 1 over lambda. Right, there's going to be some factors in there, and I might be missing a squared or something. In fact, I'm pretty sure I'm missing a squared. But this is the general idea, that when you make those regularization parameters large, what you're doing is you're penalizing having large values, which means that you're saying that the prior gets narrower and puts more of the mass close to 0. So when we turn an optimization problem into a probabilistic inference problem, regularization becomes a prior. That's a basic connection between probabilistic inference and other types of optimization problems. And so our regularization parameters in this plate diagram become priors on the distributions of these U and V matrices. So far, so good? So then, so we're doing the same thing. We're just thinking about it a little differently, and we're using a different algorithm to compute it. The reason I show you this is the basis. It's a basic component of the collaborative topic modeling system that the New York Times uses, and it's, a bunch of other people use, presumably. All right, so this highlighted stuff is what I want to show you. All right, so there's the minimization we just saw in the optimization formulation. In the probabilistic formalization, basically we're pretending that the way that these observed ratings get generated is from a probabilistic model. And by the way, pretending that something is generated by a probabilistic model is how we normally do probabilistic modeling. When we are trying to figure out how many cars are passing through an intersection, we say, okay, well, let's pretend that we decide when cars come by drawing from a Poisson distribution. Right? So this is normal. This is how we do probabilistic modeling. We say, okay, let's pretend that the ratings come from this process. It's a little more complicated process, but it's the same idea as pretending that cars come from a Poisson distribution or test scores come from a normal distribution or whatever model you have. We say for each user, we pick some topics, normally distributed with variance proportion to 1 over lambda, which is what I just showed you, right? So there's a wider variation in the topic values when lambda gets smaller. And then for each item, we also pick some topic values for that item based on its parameter. And then what we do is we multiply the topics of the user times the topics times the item, and we pick from a normal distribution on that, and then this C thing is a noise term, basically. So some variation. And that's it, right? So that's the idea, is that we pick some topics for the users, we pick some topics for the items, and then and when we pick them with a distribution of this width, and then we multiply them together and add some noise, and that is the rating that we observe. So it's a really, really similar idea to our normal matrix factorization. We've put this in probabilistic terms. And the advantage of doing this is now we can use all of the machinery of Bayesian inference. Right? So we have standard ways of estimating the probability distribution of these latent factors. That is to say, the inference is going from the R to the V and the U. Right? That's what we want to do to factor this matrix. And then when we have the V and the U, we can generate predictions just by taking a dot product. We can do that with the standard like Monte Carlo Markov chain methods that we use for Bayesian inference. How many of you have done that, by the way? Looked at MC inference for Bayesian models? Okay, a couple of you. So before the break, just to prove to you that I'm not making this up, I want to show you an article on the Facebook blog talking about how they do it. So here we go. I'll just scan through this really fast. Collaborative filtering, so that's the name of the algorithm that we've been talking about. So the item set is pretty complicated. Pages, groups, events, games, and more. Best recommendations come from people who have similar tastes. In other words, a taste is a topic in the language that we've been using. Predict how someone would rate an item. Right? It's exactly the same thing. Their problem is that they have 100 billion ratings and 1 billion users. So the standard algorithms don't work very well. And so they need to do a distributed algorithm. And so they talk about this a lot. Oh, matrix factorization. There we go. Oh, hey, that looks familiar. Right? They have 1 regularization parameter instead of 2, but there it is. They solve it using a gradient descent algorithm, which basically you perturb each value slightly and try to take the perturbations that roll you downhill, reduce the error as fast as possible. They talk about a bunch of different algorithms, And then they talk about how to do this in a distributed way. And what they end up with is they break the users and put them on different machines. So there's a different group of user on each worker machine. And then they split up the items as well. And they run this estimation with this set of users and this set of items. And then for the next time set, they cycle the items. So in other words, they keep the users fixed. So in other words, they keep the user tastes or user topics on the same machines continuously while cycling the items between machines. And at each point, they estimate a chunk of this matrix. So if I have these users and these items, then those users and those items can be used to estimate some piece of the matrix, right? So I multiply these things together. That gives me predictions. I compare them to the ratings that I actually saw. That gives me the error term. I take the derivative of the values that I have with respect to the error term. That gives me a gradient. I take a step in that gradient to try to reduce the error for these section of the matrix. And then I try it again on this machine with the same users and a different set of items, which means I'm now estimating this block, while one of the other machines, which has a different set of users, was estimating this block and is now estimating that block. So there it is in reality being done at scale in a distributed algorithm. Bringing this back to journalism. Why am I telling you all of this in the journalism school? Because this is it, folks. When people bitch about the news feed and say that it's tearing us apart, it's only showing us popular items, it's making filter bubbles, it's rewards clickbaits, and we'll get to that today. We'll talk about all of the complaints that you can level against the recommendation system. This is where it comes from, okay? And if we want to fix these complaints, we have to design a better algorithm. So it's important to start with what we are actually doing now. Okay, good work, being more or less on time. We're 1 minute late. Okay, so now we're going to talk about the New York Times recommendation algorithm. Our discussion is going to be based on this post from 2015. Also, Alex has actually come and talked to our class in previous years. He wasn't available this year. You know him?
No, I'm still so
Like just trying to say not this Alex.
Different Alex, Alex Spanger. At the time that this was built, this powered the little recommended for you box. The recommended for you box is no longer on the homepage. In fact, I think it's just gone. But now this powers personalization on all of the section pages. So if you are logged in and you go to the home page or you go to one of the section pages, those recommendations or those stories that you see will be in part based on the recommendation algorithm.
Are you sure what that looks like? Or maybe we don't know. I don't know. I haven't logged into the New York Times.
Yeah, right. So when you look at it, so what's actually happening is rather than when you're logged in, when you look at the New York Times section, you will see not just some combination of what the editors think are the hot stories and what the algorithm thinks that you are likely to read. We're also going to be looking at a snapshot of the algorithm circa 2015, 2016. This stuff is constantly evolving. So I'm not going to say that this is what the New York Times is doing today because I don't have details of what they're doing today. But this is what they did recently. And as you'll see, it's a pretty general method. And if you start reading this post, which is again linked from the syllabus, you'll see they talk about two problems. So initially, they had a content-based recommendation, which was just based on keyword tags. then they talk about some problems here. You can imagine a lot of these criticisms would apply to TF-IDF as well, right? So these are algorithms which use the text of the article to try to figure out what category it's in, look at what categories you've clicked on. Maybe what you do is you keep a vector of, which is the centroid of all of the articles that you've read, and you look at the distance between that vector and the vector for any particular article, and you rank it by closeness. So if you read a lot about bees, then it will recommend you bees articles. This has some problems. One of the big problems is that it doesn't give you articles about topics that you're probably going to be interested in but don't know you're interested in. Collaborative filtering is what we just looked at, right? It's the user item matrix. It's matrix factorization. And it can give you an article about Polish cinema even if you normally only read articles about bees, if it discovers that all of the people who like the same things as you also like Polish cinema. So maybe people who like bees also like Polish cinema. It will figure that out by looking at what other people like you are reading. Okay? But collaborative filtering has a big problem, which is, this is often called the cold start problem, which is that if nobody has yet read an article, we have no information about it. So it says right there, this approach fails at recommending newly published unexplored articles. Articles that were relevant to groups of readers but hadn't yet been read by any reader in that group. So, in 2011, there was this paper published called Collaborative Topic Modeling, which combines the two techniques. And that's what the New York Times Recommender is built on, and that is what we're going to be studying. So here's the idea. There's different ways to do filtering. So we've talked about content recommendation. That was the first class with TF-IDF and stuff. There are no users in content filtering. We've talked about collaborative filtering, which I think of as part of the broader class of social filtering, which is you use user signals to determine what you see. And so actually, I would say that Twitter is in this class as well. You see stuff from people you've followed, and actually algorithmic recommendations from people you haven't followed, unless you've turned it off, like I have, because I just want my reverse crom, damn it. Or even the Reddit ranking algorithm that we looked at. It is also possible to build a recommender that uses both the content of the item and how users are reacting to it, and that's what we're doing. So here's the idea. They're distinguishing between what they call in-matrix and out-matrix prediction. So in-matrix prediction is the collaborative filtering problem that we just talked about, and where we're asking how a user feels about an article. Out-of-matrix prediction is when we're asking about how a user feels about a new article, where we have no information at all. So collaborative filtering can't really do out-of-matrix prediction because we have no information about those rows of the matrix, and therefore this, what topic that item is and so forth. So we basically have no information on these rows in the item matrix. So we can't run our classic algorithm. It's underdetermined. On the other hand, we know the content of the articles. We know the topics in the articles, so we could predict that way. So the goal is to combine these two. So we looked at this last class. This is LDA topic modeling. This again is a very, it's all sort of the same idea of a latent variable, right? So what this is saying is that each document is a mixture of topics, which is this. Each word is a particular topic, which is this. What we actually observe is the words, and then how we pick the words once we know the topic is Oh, I see. When I slide the mouse, that's why it keeps advancing when I don't mean to. How we pick the words is each topic is a set of words. And it's roughly akin to factoring the term document matrix. It's sort of a probabilistic form of that. And then we've got these, what they call them hyperparameters, which you will play with a little bit in your assignment. So this is just modeling the content of the documents. This is just modeling user behavior. We put them together, and we get this horrifying diagram. Okay. So who is horrified by this diagram? Yeah, okay. When I first looked at this, I was just like, what? So the red annotation is all me. This is me scribbling notes to help me understand what the hell is going on here. So here's the idea. The only things we observe are the contents of the documents and the ratings that the users give. And we're going to say, well, where that actually comes from is the ratings that the users give is based on the topics that the user likes plus the topics in the document. And the topics in the document is in part determined by the ratings, right? This produces the ratings. So when we run the inference algorithm, we go backwards from the ratings to the topics in the document. But so this is the topics in the document as far as user behavior is concerned. This is the topics in the document as far as text analysis is concerned. And this arrow says that the way the document acts as far as user behavior is going to be based in part on the content of the document, right? So this arrow here is the connection between this arrow. Will it get big? There we go. The content of the document, which is this, and the way users act around it. That's the link between these two things. And intuitively, you're going to think they're going to be kind of the same, right? So if you have articles that are talking about bees, then you'll have, a high rank on the bee topic for that article. But if it turns out that it's actually talking about the portrayal of bees in a movie, then the users who like movies will also be clicking on that article, even if this doesn't use the words like film and movies. So this allows the meaning or the topics in an article to shift based on user behavior, and you'll see a diagram of that in a second. And then we go through all of the usual rigmarole. When we actually run this algorithm, what we do is we start with the content of the articles and all the previous ratings, and when we first down an article, we infer the topics for the document and also the topics for the document, or in terms of the collaborative filtering. And as we start to get ratings on that article, we update the topics that this V variable here. So basically, V starts out the same as theta when we don't have any clicks on anything, and the model allows V to drift away from theta. In other words, the topics in the document to drift from the topics we obtain from text analysis as we get more ratings.
So the R here in the New York Times recommender system is just clicks.
Mm-hmm.
And it's impacted by both people who are subscribers and non-subscribers, I assume?
No, I think it can only be people who are logged in because it needs to track what articles you've read.
Okay.
Right? It needs to figure out which user you are.
So it basically doesn't track like if you're not a subscriber, so that doesn't really matter. Like if it gets more clicks from people who are not subscribers, then
There's
that won't be taken
probably some portion of the system that takes into account overall popularity, but this model does not. So here's kind of what it looks like, and this is the diagram from the blog post I just showed you. So these are two topic dimensions. They're labeled by words. So this is exactly what we saw when we were doing PCA type stuff, or you can think of this as maybe this is a word embedding dimension, maybe it's a latent topic from LDA, but this is sort of a politics topic, this is sort of a car, I don't know, road trip topic, I guess. And every document is some point in this space. In fact, it's a much higher dimensional space than this. And if we just use and analyze it based on the topic, we get a point here. You can think of this as the theta. But if we look at how people are reading the article, right? So every user has topics as well, right? So this U is the topics for the user. So we can plot the users in the same space. And we learn that the people who are reading this article tend to be here in the space. So we push our topics for this article in the direction of the users who have read this article. In other words, we start when we have no ratings for this with this theta, and then as ratings come in and people read it, we know where those users are in topic space, and we push theta in the direction of the users who are reading it, which gives us V, which is ultimately what we take as the topic for that article. And as usual, when we want to do a prediction, we take the inner product, the dot product of U and V. So as we get more click data, the topics for that article drift towards the topics of the users who are reading it. All right?
So click data is what content plus social is again?
Yeah, social is the click data. Yeah.
Does it mean like the posts, so it's like posts about the article, posts, or like just?
No, it's not social media.
Okay.
It's social interaction.
Okay.
It does not. We are not talking about social media here. We are talking about user click-through behavior.
Did the user get pulled in the direction of the original topic, or where it stood originally?
Yeah, I guess users. Let's look at the model. So, if a user reads many articles on a certain topic, then that has to influence the topics for the user. Yeah.
Okay.
So the users will also get pulled in the direction of the article. Good catch.
But isn't that more of like a routine task kind of thing? Like once in a while you will reevaluate whether the user still fall on the top, or will it happen simultaneously? Because the articles will be happening more in a real time kind of way, but will the users also move?
Right. So in principle,
that often?
you rerun the inference on the model after every click, but you can't actually do that. So there's a question of batching this, and I think in here they talk about this more. I think in this article, this is a great article. This is worth working through in some detail. If you understand this article, you understand quite a lot about the state of the art of recommendation systems. I think in this article they talk about, yeah, here you go. Here we're modeling users. Yeah, there's lots of good detail. Yeah, I'd have to read this much more closely. They must batch it in some way. They're not rerunning on it every click. But there's a nice property of the optimization algorithm, which is it's an iterative algorithm, right? Every step you run, it reduces the error. So they can take the previous computed topics for users and articles and use that to do an update step to incorporate the newly published articles and the newly arrived click data. So they can just sort of keep this model running iteratively. All right, so that's it. I recommend you read this article. It's really, it's dense. There's a lot there. You can also read the original David Bly and Wang topic modeling article, which is this one. They originally did it for scientific articles because everybody doing NLP starts with scientific articles, which are the worst training data because it's so clean. But if you can make it through this article and that post, you will know quite a lot about how recommendation systems work. The next filtering algorithm I'm going to show you is a little bit different. Here, instead of picking articles to recommend to readers, we're going to pick tweets to show to journalists. This was a system that Reuters built and has published a bunch about called Reuters Tracer. And the idea is you ingest the Twitter fire hose. I think they are not quite the Twitter fire hose, but lots of tweets anyway. And you try to find stuff that is newsworthy. All news organizations at this point have some process for sourcing stuff from social media. This is a slide. You can tell from the image quality I was in the back and cleaned it up. But I've never seen a chart like this. I really love it. These are all of the steps that the Associated Press goes through to verify content. And in fact, there are now entire books on this. There is a book called the Verification Handbook, which was written in collaboration with the BBC. And this is an entire book on best practice for verifying stuff coming out of social media. And it has a lot of steps. So for example, you have to contact the person who posted it, both as a verification action, where did you get this from, that sort of thing, but also to clear it for copyright. And then the AP has a bunch more steps, which I think are fascinating. So you look at the sources history, find the earliest example, look at the sources history, actually talk to them, compare with AP reporting. So you've gone through all of this effort to have reporters on the ground covering stuff. Does this match what they've seen? Check with language experts. For a global news service, it's not going to be in one language, and so you have to make sure it's the language it's supposed to be, and dialect is correct, and you might pick up discrepancies in slang or word usage. And then there's this verify context step, which could be sort of arbitrarily huge. So there's this whole step. But the first thing you have to do is find it and then find the earliest version. And so that's what Reuters Tracer tries to automate. This is what the system looks like. There's a bunch of columns they call them channels on different topics. There's one that's just called news, and it just tries to find news in general. Each of these is a story cluster. Where does it show it? Somewhere in this interface it tells you how many tweets are in that cluster. This little star is a newsworthiness star. So it tries to actually figure out, okay, not only is this news, but this is the sort of thing that Reuters normally covers. These dots are a veracity score. It tries to figure out how likely it is for something to be true. These little numbers, that's how many tweets in that group. So I think 3 is the minimum here. So it tries to find a cluster of tweets on the same topic and rank it for veracity and newsworthiness in real time across all of Twitter. And it does sort of tagging stuff as well. It tries to assign categories to it. Here's the basic architecture. First, we throw out the things that aren't newsworthiness. So we don't care about people just chatting about stuff. We want events happening. We group all of the tweets into events. We assign these various scores, and then we map against various queries and alerts that reporters have set up previously. Here's a more detailed system diagram. This stuff that is in the A box is at the tweet level. So for example, we throw out spams. They call this the chit-chat filter. We rank it on how likely is it to be an actual event rather than just people talking. And then these are clusters. We group the tweets into clusters. We do more spam filtering. And then we do, for example, event verification. How likely do we think this is to be true? Newsworthiness ranking, topics. Each of these is a machine learning model. That's a machine learning model. That's a machine learning model. That's a machine learning model. There's like a dozen models in here to make this all work. It's quite a sophisticated system. One of the first models is try to break things into events or not events. And so they have this scale, which I think another researcher developed. And so they have a classifier, which is, these are all, I don't know exactly what they're using, but they're score classifiers, right? So it outputs a score like logistic regression, like where do I think it falls on here? It's a difficult classifier to build because the input data is extremely unbalanced. Almost everything is not interesting. So, it's sort of 1,000 to 1 on the left to the right side of the diagram. So it's actually quite difficult to build a classifier because a small false positive rate will just swamp the system. Right? If you have a 1,000 to 1 ratio, then a false positive rate of 1% means there's going to be 10 times as many false positives as true positives. So it's a difficult classifier to build. And then they do all of this data to time it against what reporters are already doing. So they compare both versus Reuters and versus other things. Let's see, how does this work? I think negative ones are where the algorithm is faster. And they're comparing it on 3 different types of stories. These are ones that we know are coming. And interesting, they're comparing it. They're also global news organizations, so they're comparing it to non-English speaking locations because one of their hypotheses is that this is really going to help source news from other countries where they don't have a lot of reporters who speak that language. And events that were not extracted from Google. I have to read the paper again to know exactly what that is. But anyways, this shows you that a lot of the time it's significantly faster, right? So like up to an hour faster. Oh, that's all of that I have for this paper. So this thing has dramatically sped up their reporting on a fairly large set of events, which for Reuters is extremely important because they are a business news source. So getting a couple minutes ahead can mean a lot of money to their customers, especially if they're doing algorithmic trading, which we're going to talk about repeatedly in this class, including today. All right, questions on Reuters Tracer? There's a couple really good articles about this, actually.
So what team developed it? They must have a huge data science department.
Yeah. There's an internal research team and software team. I mean, Reuters is almost unique among news organizations in that they have a lot of money and a lot of technical talent. So they can afford to build these big systems. I was at when I was at the AP, actually, my boss at one point asked me to look into building a system like this, and I was like, well, I'm one guy with responsibility for getting the news out each day, so I don't think I can get very far with this. But yeah, they've built this over several years.
And this is only used by them.
Yeah. There is a similar system that is public called Data Miner. Which you can use to basically very advanced Twitter search, including over archives and event detection, all of this. It doesn't do veracity ranking or newsworthiness detection. It's not tuned for news. And actually how they tuned this system is they took a whole bunch of events that occurred on Twitter, a subset of which were events that were covered by Reuters, and they trained a model to predict which events would actually be covered by the journalists. So I find this fascinating because it's one answer to the question of how do you decide what makes it through the filter. And what they've decided is what should make it through the filter is what currently makes it through the filter by human journalists. Now, it's not a bad or a wrong answer, but it is going to replicate whatever biases the humans have. And when I say biases, I don't even mean that negatively, right? There are reasons that journalists cover certain topics. For example, their customers are interested in certain topics. But there are also going to be bad reasons for covering and not covering things. Whenever we are building filters, we have this question of how do we decide what news is, which is a fundamental problem. And there's basically only two answers. You can decide based on what journalists actually do, or you can try to build it from first principles in some way, right? And you end up writing these rules like, well, if more than 3 people are killed, then we should probably cover this story. Which seems, I don't know, that's a hard set of rules to write, right? What are the ethics there? How do you decide what gets covered? But you end up running into these problems. It's exactly the problems journalists don't normally like to think about, but implicitly do anyway. There's lots of research showing that. So by the way, not all murders make the news, right? It's depending on the city between 30 and 70%. It is skewed towards in exactly the way you would think. So a murder is more likely to make the news if the victim is young, white, female, famous. There's a particularly violent method. It's a sex crime, or there are multiple deaths. Exactly what you would think. Doesn't seem quite right. I think some of those are justifiable in some way. But if you're not going to cover everything, you have to articulate some principles. And normally we don't articulate the principles, and we just have this sort of magic newsworthiness sense. And designing filters forces us to be explicit about these choices, which I think is wonderful. I think it's time that we pay more attention to these choices. Okay. We've talked so far about algorithmic filters. Implicitly, all of them involve humans because the humans write the articles, the humans click on the articles. When I say human-machine filters, I mean something a little bit different. I mean there are professional humans in the filtering process. And this is actually extraordinarily common. In fact, pretty much every filtering algorithm or filtering system that you will find is a hybrid system that has humans working in it as well. This is the earliest reference to humans working in a filtering system that I can find. This is TechMeme and MediaGazer, which are based off the same engine. And initially, it was just an algorithm scanning all of the blogs and news sources to try to find newsworthy stuff. And then in 2008, they changed it because they found that it was making mistakes. And how the system works now is that the human review runs 5 minutes ahead of the homepage. So the algorithm runs, and then with a 5-minute delay, that is copied to the homepage. And in that 5 minutes, there's a human editor looking at it and checking stuff out, reordering things, adding and deleting stuff. Right? So there's now a human editor watching the page all the time. Does anybody remember the Facebook trending module? Yeah. This is quite a story. If you dig into this, there's a long history. They finally just got rid of it. But here's what it looked like at the time. So this is circa 2016. And the idea is they wanted to news. Originally, they had human editors. For a variety of reasons, including allegations of liberal bias, they removed the editors. I think actually it was just convenient time to do that. I think actually the main reason they removed them is because they want a completely automated system so that they can run it in the 100 languages that Facebook runs in. But as soon as they did that, so you lost a few things. First, notice that there's a little summary here. That was a human written summary because machine summarization is not very good yet. We lost the summaries. We just have the entities now. And it started almost instantly reporting false news as well. I didn't say fake news because, well, two reasons. One is I hate that word. The other is that Facebook's documents about this call it false news, so that's what I'm going to call it here. They eventually got this under control. I don't know to what extent they have humans in the system now. But we do have a nice set of documents which were leaked circa 2016. These are the most detailed documentation on exactly how this hybrid filtering system worked. It's a remarkable document because now that you know how the things like the topic finding algorithm might work, we also know how the humans were instructed to work with the topics that were found by that algorithm. We basically have the description of a complete, large-scale production news finding system. And this is the only public description of this sort that I'm aware of. So if you study this, you'll really learn a lot about how these systems work. And this is what it looks like. So on the left here, these are the topics that it found. And I wonder if I can zoom in here. I can just do this. Here we go. So these are the topics that the trending algorithm found. It just looks at stuff that people are sharing. And sometimes it'll find a weird headline. So for example, here it said Denver Broncos, hashtag Broncos, and it said actually, let's call this the Indianapolis Colts. And you can see this whole system they had for editing it. So the importance, you can write a headline, it shows you how to appear, you get to pick the URL that that link goes to. So it's kind of like the algorithm finds a cluster of trending things, and then the human reviews it and sets it up. And there were instructions like, only include topics that are actually about a real-world event, as opposed to just a bunch of people talking about something. And it's actually quite a long document, and it's pretty, I don't know, I thought it was pretty fascinating to read. So here's the document. Nicely leaked. And they built it into 3 different teams. So they had this whole pipeline built out of humans. So throw out topics that aren't real world, remove duplicates, and it tells you how to use all of these tools. Their process today is completely different. I don't actually know what they're doing, but I still think this is pretty fascinating. And look at the problems they're solving, right? So that the thing has to have a recognizable name. That's a very difficult thing to do algorithmically. You're supposed to fix these problems, right? So it might give you a headline like this, and you turn it into that. This is one type of human participation in topic filtering. Uh-oh, where'd we go? There is another really important type, which is comments. Every major platform now has a large group of human comment moderators. And of course, the comment moderation policy is, along with the algorithmic design, controls what is visible. And so if you are concerned about ideas like public discourse, then these rules are important. And this is actually a nice little quiz that the Times published a few years ago. They turned it into a little game where they showed you a bunch of stories and you had to approve or reject. And in this case, no, we don't allow name calling. And these are designed to showcase a lot of the difficult calls. I think that's okay. Yep. You can criticize the Times. Apparently you have to explain your reason. And so on. And I actually, I think it's great that the Times published this, that they published their guidelines and they really got ahead of this discussion of what are you allowed to say. Facebook did not. And so they took a lot of criticism for, they're deleting this, they're censoring that, and it was very hard to tell if those were policy or isolated incidents. Eventually, The Guardian published leaked documents. And this is from The Guardian story. It talks a little bit about what the guidelines say. Reading these guidelines is super fascinating because you have to deal with all of this really gnarly stuff that you wouldn't even think about. The first thing to say about comment moderation policies is that it's really complicated. You're balancing a number of factors, including freedom of speech and versus hate speech or harassment, but you're also violence, porn, law enforcement, and you have to make it economically feasible too, economically and technically feasible. So actually how all of these systems work is you have a machine learning model which picks stuff which is questionable, could be porn, could be violence, and then that goes to humans to make a final call. But these are fairly nuanced calls, right? Some photos of non-sexual physical abuse and bullying of children do not have to be deleted unless there is a sadistic or celebratory element. That's quite a detailed rule. And you may or may not agree with any of these rules in particular, but I hope this gives you a sense of how complicated these rules have to be. Including, look at this, anyone with more than 100,000 followers is a public figure, which denies them full protections given to private individuals. That is precedent that comes from journalism. So laws around privacy are different if someone is a public figure. Privacy and, so for example, criticism of a politician, that's okay, right? But criticism of a private individual is treated a little more skeptically under the law.
Well, it's interesting that they treat Trump as a protected category.
Yeah.
But I think that's because it's his national security.
Yeah.
Yeah.
Yeah,
If you say something
but what other protected categories are there?
Guidelines for content moderation follow very closely the legal categories, which leads to some surprising things. So threats against children, not a particular child, but against children in general, there was one version of the Facebook content moderation guidelines that said that's fine. All right, well, doesn't have to be removed, right? That's the thing. That's the problem with these sorts of guidelines is that they immediately spark the idea that Facebook thinks it's okay to have bullying content. It's like, well, no, they don't necessarily think it's okay. They think that it shouldn't be their job to decide to remove it from the platform. So this was leaked. Eventually, they posted this document a couple years later. So I'm of the opinion that if you are running a large-scale filtering algorithm, you need to very quickly publish your moderation guidelines. This stuff is complicated. It's difficult. A lot of problems can be avoided if you're transparent about what decisions you're making. Of course, you're sort of damned if you do, damned if you don't, because nobody's going to agree. You're going to take flack whatever choices you make, but you have to make choices. So you gotta document them. And I think it's interesting to note that the New York Times did the comment moderation quiz 2 years ahead of when Facebook published this community standards document. So I think they had a better sense of their responsibility towards the community in this way. Although Facebook has a much, much more complicated problem than the New York Times, because they operate with a much wider variety of users and a much wider variety of political contexts, and at just an absurd scale. We're a billion users, right? So we're talking like 10 to the 5 difference in scale. Facebook has tens of thousands of moderators worldwide. There has been a lot of criticism of filtering algorithms in a variety of dimensions. We've already talked a little bit about the what should you see dimension, which is a really important dimension. I want to talk briefly about filter bubbles. Who's heard the term? So people started talking about the idea of filter bubbles back in the 90s. Nicholas Negroponte, who used to lead the MIT Media Lab, had this concept called the Daily Me. He foresaw personalized news and foresaw that it could lead to a narrowing of vision.
The daily what?
Daily Me. You read the Daily Me instead of the daily news. Now, polarization is real. I'm going to show you a few slides to suggest this. This is, each dot is a political book. This was during the 2008 election. Each arrow is people who bought this also bought that. So you can make this diagram just by tracing books on Amazon. And you see that they break pretty much into red and blue books. And this is not content analysis. This is purchasing decision analysis. So people buy one or the other. This is a similar diagram from the, Twitter. I think this is retweets as opposed to following. And the colors are assigned by a classification algorithm. And you can see that the network structure is such that there's a lot more within group than cross-group ties. This is a more recent analysis in a different context. This was a couple of years ago when there was fighting in Gaza, and Gilad Lotan, who's now chief data scientist at BuzzFeed, built this. And this is the co-occurrence of Twitter, Instagram hashtags. So each circle is a tag, and 2 tags get links between them and therefore are placed near to each other if they co-occur on many of the same images. And you can see there's basically 3 different clusters here. There's the pro-Israel, pro-Palestinian, and then connected and related to the Palestinian but distinct is a religious cluster. Other way around, actually. This is the religious cluster. This is the Palestinian cluster. So polarization is real. You can see this network structure in society in almost any place you look. Anytime you have a political topic, you will find these types of cluster structures. People do sort into tribes, absolutely. Always have. There's lots and lots of research about that. But this doesn't mean that there's a filter bubble necessarily. Or more precisely, it doesn't mean that our filtering algorithms are causing the bubble. In fact, the evidence that our filtering algorithms are causing people to only be exposed to agreeable viewpoints is quite weak. So here's the idea of the bubble. This is an Eli Pariser quote, and he wrote a book called The Filter Bubble. And what he's saying is that what people care about is shaped by what they see, and I think the key point here is that you get a feedback loop, in principle. If you only read articles about bees, then the recommendation algorithm will only show you articles about bees, and you're never going to care about automobile safety.
It seems rather presumptuous to think that algorithms would create tribalism. I don't know. It seems
Yeah.
like something mathematicians would come up with.
Or cultural critics, actually, is mostly where it's
Right,
came
right,
from.
right.
It's actually, I think, the reverse. I think the mathematicians are the one debunking it. Or political scientists. There's a bunch of skepticism on filter bubbles these days, but that took a few years to start building. And you will still find a lot of breathless articles that say that Facebook is splitting us apart without citing any evidence to that effect. In part because it's hard to get the evidence, which is a problem. So I'm going to show you a few different types of evidence to argue against the idea that filtering algorithms are driving tribalism. Which is not to say that they couldn't be used to diffuse it, right? To say that algorithms are not driving people apart doesn't mean that we shouldn't try to tune the algorithms to bring people together. It just means that they're not the problem. They might still be the solution, or part of the solution. So here's one type of evidence. This is polarization in voting behavior. So this is polarization at the elite level as opposed to the citizen level. But you can draw similar graphs for population attitudes. And the thing I'd like to point out is that the recent rise in polarization started well before the internet. Okay? So whatever was causing polarization to increase in the 80s and 90s was not Facebook. Here's another very interesting study. The increase in polarization is larger among people who are not online.
What's polarization measured?
So there's a variety of ways to do it. You could, for example, use, and I think this is what they did for this, data from the General Social Survey and look at clustering of attitudes. It's a great question. Polarization can be measured a bunch of ways. One way you can do it is take a bunch of questions on, do you think the government should spend more on the environment? How do you feel about abortion? How do you feel about gun control? You just take a bunch of political issues. And if you do a PCA plot of answers on that, you'll find clusters. Now this is very interesting because why should how you feel about climate change tell me how you feel about abortion? There's no logical connection between those topics, but there is a cultural connection. And the higher the correlation between separate topics, the higher the polarization. So you're looking at how well all of these different attitudes collapse into a single linear scale. In other words, how much of the variation is captured by the first principal component. And if that principal component captures most of the variation and the second component is much smaller, that tells you that basically people are answering these questions on one axis. And so that gives you a measure of the polarization. You can look at the distance, and you can look at the ratio of the size of the first axis to the size of the second axis. Or you could look at cluster structure and in-group ties. There's all kinds of metrics you could use to look at this. And I would have to read this paper again to see what this one is. But by their measure of polarization, which is this index here, which combines a bunch of these scores, people who use the internet more, which is this blue line, or in this case, younger people, again blue, had a lower increase in polarization. So that's kind of a problem for the theory that social media use is driving an increase in polarization. Another difficult factor here is that putting information in front of someone doesn't necessarily make them read it. So this is from an internal study at Facebook, which was on diversity and polarization, which is a fascinating study. Now, it comes with a big plus and a big minus. The big plus is they used real Facebook data, so they don't have to guess or use proxies or use Twitter data or something. The big minus is it comes from Facebook, so it's hard to say what's de-emphasized or omitted. But sure enough, so on the left graph is sort of ideologically what they call cross-cutting, so showing left content to right people and vice versa. And when you do that, so potential means what articles are available. Exposed means they actually saw it in their news feed. And so you can see that the news feed shows slightly less cross-cutting than ideologically aligned stuff, but not hugely less. And mostly that's because of the large number of weak ties. It's because your Facebook friends are not as homogeneous as you might think they are. And the people who are not close to you on Facebook, you're not close to all of your 500 friends, which means most of the people who are sharing content that might appear in your feed are actually fairly different from you, or fairly diverse. And so even though you see stuff from your close friends more, because your weak ties far outnumber your close friends, you actually see quite a lot of stuff from them. This is also why you get jobs through weak ties. It's because there's a lot of them. And so what actually happens is you get fair exposure to diverse opinions, but people do click on it less. That effect is real. So I don't think that social media is driving polarization. I do think it still plays a role in potentially resolving it. Which leads us to really the entire point of this whole class, which is I want people to design better filters. In fact, one of the former graduates of this program is now working on the Facebook newsfeed, which makes me very happy because I hope they've taken some of the values that we discussed. First, I want to talk about what is the information available to build a filter. So let's make a list. I've sort of sorted it into 3 categories in this slide. But in each of those categories, there's a huge amount of data. So if we are building a recommendation system for, let's say, articles with text content, what information do we have to recommend something? Let's make a list. Yell it out.
The clicks, ratings, the things that we have, like, to make decisions on the rating.
Yeah, what information do we have to build a recommendation algorithm? What are we going to feed into the algorithm? Viewing, sure. So
Clicks,
viewing history. There's 2 types. Yours and others. Okay, what else? Yep, so the topics in the text. Yep.
And then user preferred topics.
Topics from, let's say, topics from clicks, right? So this is classic collaborative filtering, that's classic topic modeling. Okay, what else? Think of everything we've talked about in this class, right? All the algorithms we've looked at. There's dozens of factors we talked about.
Shares and retweets.
Yeah, so that's maybe subsumed in here, but let's just write it. Shares and retweets. Okay, what else? What else is news, or what else is Facebook personalized by, for example? Yeah, let's call it location. And more demographics, right? Your age, sex, and so. Oh yeah, expressed interests, right? So many filtering algorithms, you can say, I'm interested in this. So Google News will do that, for example. And other user controls, right? You can turn on and off algorithmic recommendations in Twitter.
Stop following.
What's that?
You can like stop following certain people in your newsfeed.
Yeah, exactly. So let's shorthand that by saying social graph. So stop following is different. That's an expressed interest, but the structure of the social network is used as well.
Device use patterns.
Ooh.
So like when you're using.
Yeah, and like
what you're using.
There's something that'll look at if you click on a notification and it'll stop serving notifications based off of how often you respond to that. So
Okay, so is that usage history or is that? I think so. For example, what device you're on can be right. Device, time of day. Right. So if I'm reading on my iPad at night versus reading on my phone on the subway in the morning, might want different things. Yeah, exactly. If you have my location, you get even more. You know I'm at work, right?
I think interestingly, like a lot of maybe the news and like literature culture of New York is created by the fact that there's a public transportation system that forces people to be without internet access for like an hour.
It's a good theory. We'll see what happens when they introduce Wi-Fi on trains. One that no one has mentioned, but this is the first one we looked at, is recency. How long ago was this article posted?
Also, like the news context.
News context.
Like the context is the information that's being published, and how relevant it is to what's trending, I guess.
Oh, that's good. Yeah. So, what's trending? That's great. / context. Source. Yep. That's an obvious one. That's an important one. Yeah. Right. The more we do this, like it's hard to actually exhaust these. There's several dozen factors. What else?
Like SEO stuff, like number of links to the page.
Yeah. Right. Okay. So SEO, or let's say page structure. So, for example, Google penalizes slow loading pages in their rankings. Yeah.
Has usage patterns up there anywhere?
We have viewing history.
Yeah, but like how long you're browsing, or I guess that would be time of day that it would fall in the same category. But like how long you're browsing absolutely would determine what type of articles are put your way. If you average like 2 minutes, 3 minutes on Facebook, they're probably not going to put long form articles.
Oh, so you're saying if you can predict how long the user will be on using your app.
Content consumed per visit, right? So if you have a short visit time, you're probably not going to get long content thrown your way.
Yeah. Wow. Okay.
And the kind of content, like multimedia versus text.
Predicted visit time. I'm just going to say content, long, short, video, text, etc. Okay, we'll stop there. The point is there's a lot of signal in here, a lot of stuff. And I mean, it basically breaks down into this, right? So stuff about the item, stuff about me, stuff about other people. And so I've stated the filter design problem in this way. We want a rating or a relevance of a particular story to a particular user given these sets of information and also the previous results. Right? That's actually one we didn't put on this list, but have I shown you this before? Have I shown you something like this before? So Facebook definitely tracks that. It tries not to show you similar things too much. Another way to state the filter design problem is in terms of the goals. So it's not just a mathematical function, it's an algorithmic object, and in fact, algorithmic plus human object, because you have to write moderation rules and so forth, designed to produce particular outcomes. It has to be both economically viable and technically feasible, and we hope also has some sort of normative goals, both for the person, this is a good product for me to use, and the society, this is improving public discussion or whatever, however you want to talk about that. There are different ways of, sorry, I know we're running over time here. We'll wrap up in just 1 minute. There are different ways of talking about what it means to have a good filtering algorithm. This is one that Twitter has been talking about. this idea of conversational health. They have ideas of diversity here. They have ideas of shared reality. You know, are we all talking about the same things? These are sort of filter bubble ideas. There are multiple different definitions of diversity. When you start digging into this idea, you can connect different ideas about diversity to different theories of political participation. So you might say that diversity means, I should have a variety of opinions. You might say diversity means I should be served exactly those things I've expressed an interest in, or I might want to be interested in. Or you could say it should challenge people, right? I shouldn't necessarily have balanced content, right? This is a more radical theory of what a filtering algorithm should do. And each of these could be turned into an algorithm or a modification on an algorithm.